The greatest breakthroughs of tomorrow might already be lost in yesterday. This is the mystery of lost materials, ancient substances with incredible properties we still cannot fully replicate. By the end, you will understand how these forgotten recipes could transform modern science and reshape our world. How did Roman concrete survive 2,000 years in the sea? And what secret was so dangerous an emperor had a man killed to suppress it? We are about to search through the ashes of history for blueprints to a better future. What forgotten innovation do you think could change everything if we found it today? This distinction between an old object and a lost material is crucial. A rusted sword in a museum is a relic, but a sword described in ancient texts as being so flexible you could tie it in a knot, yet so sharp it could slice through falling silk, that points to a lost material. The object itself might be gone, but the record of its impossible performance remains, taunting our understanding of physics and metallurgy. These substances occupy a strange middle ground. They are often mentioned with such specific, repeatable details across different historical accounts that they transcend mere legend, yet their full recipes have vanished from our collective workshop. The loss is rarely a single dramatic event, though events like the burning of the Great Library of Alexandria represent a catastrophic amnesia for humanity. More often, knowledge fades quietly. A master artisan passes away without an apprentice worthy of the secret. A trade guild guards its methods so fiercely that when the guild dissolves, the methods dissolve with it. An entire civilization collapses, and its most advanced technologies become indecipherable to the survivors, slowly relegated to the realm of myth over generations. So when we speak of lost materials, we are not chasing ghosts. We are following a very real, very cold trail of evidence. It is a scientific detective story where the crime scene spans continents and millennia, and every clue is a fragment of pottery with a strange glaze, a line of poetry describing a fabric that shimmered like water, or a metallurgical anomaly in an ancient blade that simply should not exist with the technology of its time. This framework turns our exploration from a passive review of history into an active investigation. We are not just learning what was lost, we are learning how to look for it. That feedback loop between history and the laboratory is where the magic happens. A single line in an ancient text becomes a hypothesis, and a modern spectrometer becomes the tool for testing it. This is why lost materials captivate such a diverse range of minds. For the historian, they are not just curiosities, they are profound challenges to the story we tell ourselves about human progress. We often imagine history as a steady, upward climb from primitive to advanced. But what does it mean when a 2,000-year-old sample of concrete outperforms its modern counterpart in a specific, crucial way? It suggests our path is not a straight line, but a winding road with forgotten detours leading to peaks we have yet to rediscover. These materials force us to re-evaluate entire civilizations, to see them not as precursors to us, but as innovators in their own right, solving problems with a creativity we have misplaced. For the scientist or engineer, these lost substances are like anomalies in the data. In any field, the most interesting discoveries often come from the outlier, the result that does not fit the established model. A Roman glass cup that demonstrates incredible resilience, or an ancient steel blade with a nanostructure we struggle to replicate even with electric furnaces. These are the ultimate outliers. They are empirical proof that a certain combination of strength, flexibility, or durability is physically possible. The recipe may be lost, but the existence of the final product is a beacon. It tells researchers, do not give up on this idea. It has been done before, which means it can be done again. This transforms the quest from a speculative gamble into a targeted investigation with historical precedent as its guide. And then there is the element of sheer beauty, the sublime quality that elevates these materials into legend. Consider Tyrian purple, the legendary dye of ancient Phoenicia. Its color was not just a pigment, it was a spectacle, extracted from thousands of sea snails through a notoriously complex and foul-smelling process. It produced a vibrant, deep purple that did not fade with sun or washing. To wear it was to wear sunlight and the sea, a color so rare and radiant it became synonymous with royalty and divinity for centuries. Its recipe faded with the fall of the Roman Empire. We know generally how it was made, but the exact alchemy that yielded its specific, unmatched hue is a secret the Mediterranean still keeps. This is not merely a lost chemical formula. It is a lost art, a lost sensory experience. The drive to recover it is about more than chemistry. It is about touching the aesthetic world of an ancient people, understanding what they considered the pinnacle of beauty and why it held such power. So the hunt for these substances is multifaceted. It is a technical puzzle for the engineer, a historical corrective for the scholar, and a cultural bridge for all of us. Each attempt to recreate a lost material is a conversation across time. We are asking our ancestors a question, and by experimenting in our labs, we are listening for a reply in the data. The ultimate reward is not merely a new substance for our toolkit, though that would be transformative. It is the humbling and exhilarating realization that human ingenuity has always been capable of extraordinary leaps, and that our future advancements might be hidden in plain sight, waiting in the quiet records of the past. This brings us to one of the most famous and enduring of all these mysteries, a material that built an empire and defies the ocean to this day. The shimmering surface of a Damascus steel blade is not just a pattern. It is a frozen storm, a captured landscape of swirling light and shadow known as the watering. This visual signature, as beautiful as it is distinctive, was merely the outward sign of something far more profound happening within the metal itself. For centuries, the blades forged from this legendary material were said to possess almost supernatural qualities. Historical accounts, from the crusaders who faced them to the merchants who traded them, speak of edges so keen they could cleave a silk scarf as it floated to the ground, and of a resilience that allowed the blade to bend without breaking. When the last masters of the craft passed, the exact alchemy of its creation passed with them, leaving behind stunning artifacts and a mystery that defied centuries of modern metallurgy. We could admire the blades in museums, but we could not make new ones. The secret seemed irrevocably lost, a peak of ancient technology we could observe but never again ascend. Then, in the late 20th century, science finally developed eyes sharp enough to see what the ancients had wrought. Under the gaze of powerful electron microscopes, researchers peered into the very soul of a genuine Damascus blade. What they found was not just advanced for its time, it was advanced for ours. Embedded within the steel were structures we associate with the most cutting-edge material science of the 21st century. Carbon nanotubes and cementite nanowires. Think of these as incredibly tiny, incredibly strong reinforcing rods engineered at the atomic level. Their presence explained the legendary properties, the combination of flexibility and fearsome edge retention. The stunning realization was that medieval swordsmiths, working with bellows and charcoal forges, had somehow become accidental nanotechnologists. They were manipulating matter at a scale they could not possibly conceive of, guided not by theory, but by generations of perfected craft. The key likely lay in a specific recipe and a rhythmic, almost meditative process. It began with Wootz steel, a high-carbon steel imported from India in ingot form. The master smith would then subject this material to a precise cycle of heating, folding, and cooling, perhaps using specific organic materials in the forge. This careful, controlled process allowed the carbon in the steel to arrange itself into those miraculous microscopic structures. It was not magic, It was a supremely sophisticated form of material engineering, passed down through touch, sight, and experience rather than a textbook. Today, the full replication of that process remains just out of reach. We can analyze the product, but we cannot perfectly recreate the journey. Yet the mere existence of these nanotubes in an ancient blade is a revolutionary beacon for modern science. It proves that such strong, lightweight composite structures can be formed and integrated into metal through means other than our most advanced laboratories. Rediscovering the full method could unlock new ways to design alloys, not just for swords, but for the delicate instruments of microsurgery that require flexibility and a permanent sharp edge, or for the skeletal frames of spacecraft and aircraft where every gram saved without sacrificing strength is a monumental victory. The story of Damascus steel is a profound lesson in humility. It teaches us that technological progress is not a simple, linear march. Sometimes a path is walked to its brilliant end, and then the map is lost. The artisans who made these blades were solving a problem, strength and sharpness, with the tools and understanding they had. In doing so, they stumbled upon a principle of material science that we are still striving to master. Their legacy is a question etched in metal, a challenge from the past that continues to shape the materials of our future. And while one legendary metal captivates the imagination, another built the physical backbone of an empire on a scale that still defies belief. The same sea that erodes our modern ports has only strengthened theirs for 2,000 years. Roman concrete, or opus cementitium, did not just resist the Mediterranean. It formed an alliance with it, a partnership so durable that breakwaters laid during the reign of Augustus still stand today, defying waves, salt, and time itself. This was no accident of sturdy rock. It was a designed material, a technological triumph whose full recipe vanished in the slow collapse of the empire that created it. For centuries, we could only marvel at the ruins and assume the Romans simply had access to better, lost ingredients. The truth, uncovered only recently by advanced material analysis, is far more clever. The Romans were not just builders, they were brilliant chemists, and their secret ingredient was the one thing modern engineers fight against: seawater itself. Their concrete was a mix of volcanic ash, known as pozzolana, lime, and aggregates, but the masterstroke was mixing it with seawater, either during preparation or by casting it directly into the ocean to cure. This was not a compromise, it was the catalyst for a slow-motion miracle. When salt water permeates the Roman mixture, it sets off a rare and prolonged chemical conversation. Over decades and centuries, the seawater gradually reacts with the volcanic ash and lime, transforming unstable compounds into incredibly sturdy crystalline structures, minerals called aluminous tobamorite and philipsite. Think of these crystals as a living, growing reinforcement. They do not just sit there, they actively fill in microscopic cracks and voids as they form, creating a material that literally heals itself. The longer it is in contact with seawater, the stronger and more resilient it becomes. This turns our entire understanding of material lifespan on its head. Modern Portland cement, the backbone of our contemporary world, is in a constant losing battle with the elements. Saltwater corrodes its internal structure, leading to the spalling and weakening we see in aging bridges and docks, often within 50 years. Roman concrete presents the opposite paradigm. It is not a material that endures its environment. It is a material that is perfected by it. The implications of recovering this lost knowledge are staggering. Imagine marine constructions, seawalls, offshore energy platforms, or submerged tunnels engineered to last for millennia, not decades. The economic and environmental savings would be immense, reducing the constant cycle of repair, replacement, and resource extraction. But the lesson extends far beyond the coastline. The principle of self-healing, inspired by this ancient concrete, is now a holy grail in modern material science. Researchers are actively developing polymers and composites that can mimic this process, materials for bridges, roads, and aircraft that can detect stress and repair themselves, dramatically improving safety and longevity. The Roman engineers did not have our microscopes or molecular models. They observed, they experimented, and they discovered a recipe that worked so well its results are still performing their duty 2 millennia later. Their legacy is a profound challenge to our own assumptions. We often pursue permanence through resistance, building thicker walls and stronger barriers against nature. The Romans, in their wisdom, achieved immortality through integration. They built with nature, using the sea's own power to forge an unbreakable bond. Their concrete does not just stand against the waves, it is a part of the sea, a testament to the idea that the most enduring solutions may not come from conquering the elements, but from learning to converse with them. While Roman concrete built in harmony with the sea, another legendary substance was designed to dominate it with terrifying mastery. Greek fire was not merely a weapon, it was a psychological and tactical phenomenon that shaped the fate of an empire for over 700 years. Imagine the sheer terror of a medieval sailor witnessing an enemy ship unleash a roaring stream of liquid flame, a fire that clung to the wooden hulls and danced across the water's surface, defying every attempt to douse it with water, which only seemed to make it burn more fiercely. This was the Byzantine Empire's ultimate safeguard, a closely guarded secret that turned the tide of countless naval battles and sieges, preserving Constantinople when all other defenses seemed certain to fall. The secret of its composition was protected with a severity unmatched in the ancient world. Knowledge was compartmentalized, with different families entrusted with separate parts of the recipe, and the imperial workshops where it was concocted were a vault of state secrecy. So effective was this silence that when Constantinople finally fell in the 15th century, the formula vanished utterly, leaving behind vivid historical descriptions but no blueprint. Modern forensic history and chemistry point to a likely base of crude petroleum, similar to naphtha, drawn from natural surface wells in the region. To this, artisans may have added quicklime, which ignites upon contact with water, sulfur for its intense flammability, and possibly saltpeter, an early form of saltpeter. The genius, however, was not just in the ingredients but in the delivery system, a complex pressurized siphon or pump that could project this hellish concoction over a distance. The enduring mysteries that captivate researchers are its ignition mechanism, a chemical trigger that remains elusive, and its adhesive, water-resistant qualities. How did they create a substance that not only repelled water but used it as fuel? Unlocking these secrets would be more than a historical curiosity. It could illuminate principles of advanced chemical propulsion or even lead to revolutionary fire suppression techniques. By understanding the very chemistry that made a flame so persistent, we might learn how to defeat such flames permanently. Yet the legacy of Greek fire casts a long and cautionary shadow. It stands as the definitive example that lost materials are morally neutral, their value defined entirely by human intention. This was a tool of immense destruction, a technological advantage whose sole purpose was protection through overwhelming terror. Its recovery would force a profound ethical question, one that echoes into our own era of technological leaps. Do we pursue all knowledge simply because it can be found, or do we weigh the potential consequences of resurrecting a power designed solely for conflict? The flames that saved an empire remind us that some secrets once lost carry the weight of their own history, challenging us to consider not only if we can rediscover the past, but whether we should. The emperor's fear was not of the glass itself, but of the world it would create. The story of Tiberius and the unbreakable bowl, passed down by Roman historians, is less about a magical material and more about a chilling moment of technological censorship. An artisan demonstrates a drinking vessel that does not shatter when struck. Instead, it merely dents, and the dent can be hammered out again, restoring the bowl to its original shape. This was not brittle silica glass as the Romans knew it. It behaved more like a metal possessing what we would now call ductility. Tiberius, upon seeing this, asked the craftsman if anyone else knew the secret. When the man swore no one did, the emperor reportedly had him killed, fearing that such a substance would utterly collapse the value of gold and silver, the very foundation of imperial wealth and power. Whether this event happened precisely as recorded is debated by scholars, but its persistence in the historical record is profoundly revealing. It tells us that the concept of a flexible, durable, transparent material was not a fantasy in the ancient mind. It was a plausible goal, an ambition on the edge of their technological horizon. And more darkly, it presents history's first clear case where a revolutionary material was allegedly suppressed at its birth, its potential erased by a single decree. This transforms the loss from a mere accident of time into a deliberate act, a road not taken by human choice. So what could this substance have been? Modern materials scientists, looking at the description, point to two fascinating possibilities. The first is a form of ancient metallic glass. We now know that if you cool certain molten metal alloys extremely rapidly, preventing the atoms from arranging into a rigid crystalline structure, you create an amorphous solid that is strong, hard, and can have some flexibility before failing. The second possibility is an ultra-tough, transparent ceramic, akin to what we today call transparent aluminum oxynitride, a material literally brought from science fiction to reality, which is used for armored windows and military optics. Could an ancient glassmaker, experimenting with different sands, minerals, and quenching techniques in a hot forge, have accidentally stumbled upon a similar process? It is not impossible. The rapid cooling of a small, molten blob in water or on a cold metal surface could have created a tiny sample with these extraordinary properties, a fleeting glimpse of a material millennia ahead of its time. The true tragedy of the tale is not the lost recipe, which might have been a fleeting accident the artisan himself could not perfectly repeat. The tragedy is the lost path of inquiry. Tiberius saw only threat where a different mind might have seen infinite potential. Imagine if that research had been encouraged, funded, and explored. The development of durable, transparent materials could have reshaped architecture, navigation, science, and daily life in ways we can barely conceive. Today, the quest for such a material is more urgent than ever. We seek it for the smartphone screens in our pockets that constantly risk cracking, for the windows of spacecraft and deep-sea vehicles that must withstand incredible pressures, for lightweight armor that protects without obscuring vision. The legend of the unbreakable glass is a stark reminder that progress is not inevitable. It can be halted by fear, by short-sightedness, by the desire to preserve an old order at the expense of a new possibility. It asks us a difficult question. What world-changing innovations might we be suppressing today, not through execution, but through neglect, lack of funding, or an unwillingness to challenge the economic foundations of our own time? The lost glass of Tiberius is a ghost of a future that never was, and a cautionary tale that the greatest barrier to rediscovering lost materials may not be the passage of time, but the limitations of our own imagination and courage. Royalty was not just worn, it was smelled before it was seen. The legendary dye known as Tyrian purple announced itself with an odor so potent and unpleasant that the workshops of ancient Phoenicia were relegated to the outskirts of cities, a necessary exile for creating a substance of divine beauty. This was the ultimate paradox of the ancient world, a color born from rot and decay that came to symbolize eternal power and sanctity. To produce a single gram of this vibrant dye required the meticulous harvesting and processing of thousands of sea snails, specifically the spiny dye murex. The labor was staggering, the smell was horrific, and the result was a color so radiant and enduring that a garment dyed with true Tyrian purple would not fade in sunlight or wash out in the sea for generations. It was quite literally worth more than its weight in gold, a physical manifestation of status that transcended borders and epochs, from the robes of Phoenician priests to the imperial purple stripes on a Roman toga. The basic biological source has never been a secret. The snails possess a mucus gland that, when exposed to air and sunlight, undergoes a remarkable chemical transformation, shifting from a clear secretion through shades of yellow and green before settling into that deep, rich purple. The ancients mastered the harvesting and the initial vat process, but the full alchemy that followed, the precise sequence of heating, salting, and fermenting in lead or tin pots over weeks or months, is what remains shrouded in mystery. This was not a simple extraction, it was a carefully guided biochemical symphony. Modern science can replicate a color close to Tyrian purple, but we have not matched its legendary permanence. Our synthetic dyes, for all their convenience, often surrender to the sun's rays or the agitation of a washing machine, their molecular bonds breaking down over years or decades. The ancient dyers achieved a bond with the fabric that seems to have been nearly covalent, a fusion of color and cloth that resisted the relentless march of time. Unlocking that secret of color fastness is the true holy grail. Imagine the implications. This is not merely about creating a better purple for clothing. The principles behind such a stable organic dye could revolutionize fields we seldom connect to ancient fashion. In medicine, fluorescent dyes used for imaging inside the human body could be made more stable and reliable, leading to earlier and more accurate diagnoses. In energy, the quest for efficient organic solar cells, which use carbon-based materials to capture sunlight, is often hampered by the degradation of their light-absorbing dyes. A formula for centuries of stability, inspired by a sea snail, could point the way to more durable and affordable renewable energy. For archivists and conservators, the ability to protect priceless textiles, paintings, and historical documents from fading would be an invaluable gift, allowing future generations to see the vibrant past as it truly was. The pursuit of Tyrian purple, therefore, transforms from an archaeological curiosity into a cutting-edge scientific investigation. It asks a profound question: how did ancient artisans without knowledge of organic chemistry manage to coax such incredible durability from a simple biological source? Their process likely involved a slow, controlled oxidation and the use of metal ions as mordants, substances that fix the dye to the fiber in just the right sequence and environment. Each failed modern experiment brings us closer, not just to a color, but to a forgotten philosophy of working with natural processes rather than rushing against them. The dyers of Tyre and Sidon understood something we have often forgotten in our age of instant synthesis, that some transformations cannot be hurried, that permanence is a conversation with time, not a command. In a world where so much feels temporary, the legacy of Tyrian purple is a whisper across millennia, a promise that some forms of beauty are meant to last forever, and that the secret to their endurance might still be waiting, not in a futuristic lab, but in the slow, patient wisdom of the ancient world. The most haunting losses are the ones that happen right in front of us. In the final years of the 20th century, on British television, a retired hairdresser named Maurice Ward conducted a demonstration that seemed to defy the laws of physics. He held a blowtorch to a small, pale pink egg coated in a material he called Starlight. The flame, hot enough to cut through steel, played over the surface for minutes. When he finally turned it off and touched the coating with his bare fingers, it was cool. He then cracked the egg open to reveal a perfectly raw, uncooked yolk and white inside. This was not a historical account or a fragment of parchment. This was a modern miracle captured on video for the world to see, and it promised a revolution in material science. Starlight was described as a complex, non-toxic polymer composite, a putty-like substance that could be molded or painted onto almost any surface. Under extreme heat, it was said to undergo an incredible transformation, carbonizing into a lightweight, expanding ceramic foam that acted as an unparalleled insulator, shielding whatever was behind it from temperatures that could mimic a nuclear flash. The potential applications were staggering. Imagine a world where a thin layer of paint could make homes and offices fireproof, where aircraft fuselages could withstand engine fires long enough for safe emergency landings, where the protective gear for firefighters and soldiers offered a level of safety previously thought impossible. Aerospace agencies and military laboratories from around the world took notice, conducting their own tests. Reports suggested the material performed remarkably, yet Maurice Ward, the sole creator, guarded his formula with an intensity that made Byzantine emperors seem open-handed. He refused to patent it, fearing the details would become public. He engaged in years of negotiations with governments and corporations, but no deal was ever struck that met his stringent, often shifting conditions. He was, by all accounts, a brilliant tinkerer, a classic outsider inventor who trusted his own intuition over the established scientific process. When he passed away in 2011, the secret of Starlight's precise composition died with him. This is a uniquely modern tragedy of loss. It is not a mystery eroded by centuries or buried in the ruins of a fallen empire. It is a ghost from our own recent past, a testament to a different kind of obstacle to progress, the fragile and sometimes fatal link between individual genius and collective human advancement. The story of Starlight forces us to confront difficult questions about how innovation happens. Was Ward a visionary protector of a world-changing discovery, rightly wary of large institutions that might bury or misuse it? Or was he a victim of his own secrecy, a man whose desire for absolute control ultimately denied humanity a tool of immense good? The truth is likely a complex mixture of both. His caution speaks to a real and valid fear that a material of such power could be weaponized or locked away by corporate or military interests. Yet the outcome remains the same. A potentially transformative technology is now a series of unverified claims and grainy videotapes. Laboratories have tried to reverse engineer the concept, creating materials that mimic its described behavior, but nothing has yet matched the legendary performance of that original pink coating. The ghost of Starlight haunts modern material science not as an ancient myth, but as a stark contemporary lesson. It reminds us that the chain of knowledge is only as strong as its weakest link, and that sometimes the greatest threat to a brighter future is not a lack of ideas, but a failure of trust, collaboration, and shared purpose. It underscores that for all our digital networks and global databases, profound knowledge can still reside in a single human mind and vanish with it. This loss challenges us to build systems that can nurture and preserve brilliant, unconventional insights, transforming solitary flashes of genius into lasting light for everyone. And it begs a final, unsettling question in an age of information. What other miracles are we losing right now, silently extinguished not by the passage of millennia, but by the barriers we place between a great idea and the world it was meant to change? The ocean floor held more than a broken shipwreck. It cradled a ghost from the dawn of machinery. Recovered from a Roman-era shipwreck off the Greek island of Antikythera over a century ago, the corroded lump of bronze and wood initially baffled researchers. It was only decades later, with the advent of X-ray tomography, that the truth was revealed. Inside was an intricate assembly of at least 30 interlocking bronze gears, a differential system, and precisely calibrated scales, a mechanical computer designed to predict celestial events, track the cycles of the Olympic Games, and model the irregular motions of the moon. Dated to the 2nd or 1st century before the Common Era, the Antikythera Mechanism is a historical singularity, a device whose sophistication would not be matched for over 1,000 years. We marvel at its gears, but we must also ask, what were they made of? The material story here is as compelling as the mechanical one. Crafting those tiny, intricate bronze gears, some with teeth finer than a grain of rice, required a metallurgical mastery we are still piecing together. The bronze alloy itself had to be exceptionally uniform and free of impurities to be cast and worked at such a miniature scale. Even more intriguing is the device's survival. Submerged in salt water for 2 millennia, the fragments we have were preserved within a protective crust of corrosion, while organic components like its wooden frame and any potential papyrus instructions dissolved away. This raises a profound material question. Did the ancient makers employ a specific anti-corrosion treatment, a lost formula for stabilizing bronze in a marine environment, perhaps through a deliberate patination process or an applied coating? The answer could revolutionize how we protect sensitive metal components in modern subsea infrastructure or marine robotics. Furthermore, the mechanism as we see it is a skeleton. Its original casing, likely a wooden box with bronze or silver facades, and its display dials, which may have included inlaid materials or colored markers for different planets and stars, are gone. Were there materials used for these elements that enhanced its function or durability, a special lacquer to protect the engraved text, or a specific type of glass or crystal for protective covers? The complete material palette of the device remains a mystery. Solving it would do more than satisfy historical curiosity. The principles behind such ancient precision engineering, the ability to manufacture and assemble micron-level components without electricity or computer-aided design, hold direct lessons for our own technological challenges. Today, we build micro-electromechanical systems, or MEMS, tiny machines with moving parts used in everything from car airbag sensors to medical implants. We also design robots meant to operate in extreme environments, like the crushing depths of the ocean or the abrasive dust of Mars. These machines demand materials that are not only precise and strong, but also resilient against corrosion, radiation, and temperature swings without constant maintenance. The Antikythera Mechanism, a device built to model the cosmos, endured an unintended 2,000-year stress test in one of the harshest environments on Earth. By understanding the full suite of materials and techniques that went into its creation, we might uncover forgotten approaches to durability and miniaturization. Perhaps the ancient Greeks used a specific annealing process, a slow cooling technique that relieved stress in the metal and made it less brittle. Maybe they employed a lost wax casting method of unparalleled fidelity. Each clue pulled from those corroded fragments is a whisper from a workshop 2 millennia past, offering advice on how to build things that last. The mechanism is therefore a dual legacy. It is a stunning testament to lost mechanical genius, proving that the conceptual leap to complex gearing and computational modeling occurred far earlier than we ever imagined. But equally, it is a puzzle box of lost material science. Its very existence challenges the timeline of human innovation, suggesting that the path to precision engineering was not a straight line from the Industrial Revolution to the Silicon Age, but a branching tree with one magnificent, fruit-bearing limb that grew, was forgotten, and now waits to be understood anew. The Lycurgus cup does not simply change color, it changes reality depending on how you look at it. Held in ordinary daylight, this 4th century Roman drinking vessel is a solid, opaque green like carved jade. But bring a light source behind it, and the entire cup undergoes a magical transformation, glowing with an ethereal, translucent ruby red. This is not a trick of the light or a simple pigment. It is a permanent, engineered property of the glass itself, a phenomenon known as dichroism. For centuries, it was considered a magnificent mystery, a one-of-a-kind artifact that defied explanation. Then, in the 1990s, scientists placed a fragment of the cup under a powerful microscope and were met with a sight that rewrote history. Embedded within the glass were countless particles of gold and silver, but not in any form a Roman artisan could have seen. These were nanoparticles, specks of metal so infinitesimally small they are measured in billionths of a meter, smaller than the wavelength of light itself. Their presence was not an accident or an impurity. It was a deliberate, staggeringly precise act of nanoengineering, achieved over 1,600 years before the word nanotechnology was ever spoken. The effect these particles create is a dance of physics at the smallest scale. When light hits the cup, these nanoparticles interact with different wavelengths in unique ways. They scatter the green light, making it reflect back to our eyes, but they allow the red light to pass straight through. So the color you see is not a property of a dye, but a consequence of atomic architecture. The true genius and the enduring mystery lies in how the Roman glassmakers accomplished this. They had no concept of atoms, no electron microscopes to verify their work. Their process was one of pure empirical artistry, likely developed through generations of observation, experimentation, and passed-down craft. The leading theory suggests they created a colloidal mixture, a sort of molten glass brew containing finely ground gold and silver dust, perhaps from coin clippings, along with a mineral like tin oxide to help stabilize the mixture. Through a specific and tightly controlled cycle of heating and cooling, the extreme heat would dissolve the metals into the glass, and then as it cooled, the metals would precipitate out, not as visible flecks, but as these uniform, nano-sized crystals suspended perfectly throughout the material. The precise recipe, the exact temperatures, the cooling rates, and the mineral ratios remain a secret the cup has kept. We can analyze the product, but we cannot reliably reproduce the process at the scale the Romans seemingly could, as other fragments of similar dichroic glass have been found. The loss of this technique is not just an artistic tragedy, it is a technological roadblock. Today, we create nanoparticles in multimillion-dollar labs with lasers and chemical vapor deposition, processes that are energy-intensive and difficult to scale. The Romans may have achieved a similar result with a furnace, a bellows, and an artisan's intuitive understanding of his materials. Rediscovering that simpler, more elegant method could revolutionize modern photonics, the science of using light to transmit and process information. Imagine smart windows for skyscrapers that don't require complex electronic layers, but are inherently dichroic, dynamically blocking heat, inducing infrared light while admitting comfortable visible light, dramatically reducing cooling costs. Consider ultra-sensitive medical sensors that use gold nanoparticles to detect a single virus particle, manufactured not in a sterile clean room, but through a scalable, ancient-inspired process that makes them affordable worldwide. The cup demonstrates a principle we are still striving to master economically, the ability to precisely structure matter at the nanoscale to control light with perfection. The Lycurgus cup, therefore, is more than a beautiful relic. It is a silent, gleaming proof that the human drive to manipulate the material world has always operated at the frontier of the possible. Those artisans were not just decorating a cup, they were engaging in a form of alchemy so advanced its full meaning would only become clear millennia later. They worked by feel and by tradition, yet they touched a domain of science we have only recently begun to map. Their legacy is a humbling reminder that innovation is not always about having the right theory first. Sometimes it is about having the patience to observe a beautiful accident and the craftsmanship to repeat it until it becomes a miracle. In its quiet shift from green to red, the cup holds a message that the line between ancient art and cutting-edge science is far thinner and far more beautiful than we ever imagined. A library of cures can be lost as completely as a temple or a city. The pursuit of lost materials extends beyond stone, metal, and glass into the very fabric of life itself, into the forgotten forests of botanical knowledge cultivated by ancient healers. For millennia, humanity's pharmacy was the natural world, a vast and intricate landscape of roots, leaves, barks, and flowers whose properties were mapped through generations of careful observation and lived experience. This knowledge, compiled in texts like the monumental Materia Medica by the 1st century Greek physician Dioscorides, was not a simple list of plants. It was a complex database of over 600 species, detailing their appearance, habitat, therapeutic uses, and methods of preparation. Yet today, reading these ancient texts is like holding a map written in a partially forgotten language. We recognize the landmarks, but the specific paths, the precise turns, are blurred. The exact species intended by a historical name, the nuanced preparation methods like specific drying times or fermentation processes, and the sophisticated combinations of multiple plants designed to work in synergy, these details are often obscured by time and translation. This represents a different kind of loss, not of a single substance, but of an entire system of understanding, a pharmacopoeia where the instructions have faded. The most poignant example is silphium, a plant cherished by the ancient Greeks and Romans that grew only in a narrow coastal region of North Africa. Silphium was a panacea, used for everything from coughs and digestive ailments to, most famously, as a highly effective contraceptive. Its value was so immense that its image was stamped on coins, and classical writings describe it as worth its weight in silver denarii, but demand doomed it. Overharvesting and possibly climate shifts drove the plant to complete extinction by the 1st century of the Common Era. With it vanished not just a species, but a living library of chemical compounds, its exact biological mechanism lost forever, leaving modern scientists to wonder what potent molecule ancient women relied upon and how it worked so effectively. This story is a stark ecological parable about the fragility of knowledge tied to a single, irreplaceable source, yet the narrative is not solely one of loss. It is also one of rediscovery, offering a blueprint for how to consult these ancient texts. The most celebrated modern example comes from China, where researcher Tu Yao turned to 4th century texts on herbal medicine for malaria treatments. Her team meticulously studied a recipe for sweet wormwood or Artemisia annua, mentioned in a text by Ji Hong. By revisiting the original preparation method, a cold extraction process, instead of using high heat which would destroy the active compound, they successfully isolated Artemisinin, a breakthrough anti-malarial drug that has saved millions of lives and earned a Nobel Prize. This was not a lucky guess, it was a deliberate, respectful dialogue with the past, treating the ancient text not as folklore, but as a peer-reviewed paper containing a crucial, overlooked detail. This success story illuminates the immense potential waiting in other forgotten pharmacopoeias, from Ayurvedic traditions in India to the herbal lexicons of indigenous cultures worldwide. The modern fields of ethnobotany and phytochemistry are now the bridges. Ethnobotanists work with cultural knowledge holders and historical texts to identify plants and their traditional uses. Phytochemists then analyze these plants, searching for the specific bioactive molecules responsible for the described effects. This systematic approach transforms historical anecdotes into testable hypotheses. Could a treatment for neurodegenerative diseases like Alzheimer's be described in a medieval monastic manuscript, waiting for us to correctly identify the referenced moss or fungus? Might a synergistic combination of 3 plants listed in an ancient Egyptian papyrus hold the key to mitigating the side effects of powerful cancer therapies? The ancient healers were masterful experimentalists, their clinical trials conducted over centuries within their communities. They may not have known the words alkaloid or glycoside, but they possessed a deep, functional understanding of a plant's power. By partnering with this legacy, modern science does not merely plunder the past for ingredients. It engages in a collaborative investigation, using advanced tools to decode the empirical wisdom of our ancestors. The Lost Pharmacopoeia, therefore, is more than a historical curiosity. It is a living frontier. Each rediscovered recipe or correctly identified species is a testament to the enduring human quest for healing, a thread of knowledge that, though once broken, can sometimes be patiently rewoven. It reminds us that the next medical revolution might not only be found in a futuristic lab, but also in the quiet, careful study of a very old book, waiting for a new generation to understand its language. Plato gave Atlantis walls that shimmered with a metal more precious than anything but gold. In his dialogues Critias and Timaeus, he describes the lost civilization's central temple, where entire pillars were clad in a fiery, reddish metal called Orichalcum, mined from the earth of the island itself. This was not a decorative footnote, it was a cornerstone of his vision, a material so integral to Atlantis' splendor that its very name translates roughly to mountain copper or copper from the mountains. Yet when Atlantis sank beneath the waves, Orichalcum did not merely vanish as a physical substance. It dissolved into the realm of myth, becoming a symbol for any lost, superior material from a forgotten age. This creates a unique puzzle for historians and material scientists alike. Is Orichalcum a literary device, a fictional element Plato invented to convey the glory of a fictional place? Or was he referencing a real, remarkable alloy known to the ancient Mediterranean world, whose true nature has been obscured by centuries of legendary embellishment? The search for it forces us to navigate the foggy border where archaeology ends and mythology begins. Most scholarly consensus leans toward a material reality. Ancient texts beyond Plato, including later Roman writings, mention Orichalcum as a traded commodity. The leading theory is that it was a naturally occurring or early manufactured brass, an alloy of copper and zinc. In the ancient world, before the mastery of zinc smelting, such a metal would have been extraordinarily rare and dazzling. Imagine the impact of a metal with the warm, golden hue of copper, but with a brighter, more resonant ring and a greater resistance to the green tarnish that slowly consumes copper objects. It would have seemed magical. Recent archaeological finds have added fascinating clues. In 2015, a shipwreck off the coast of Sicily dating to around 600 BCE yielded 39 ingots of a mysterious reddish metal. Analysis showed it was an alloy of copper, zinc, and small traces of nickel, lead, and iron. While not a single, uniform recipe, these ingots prove that complex copper-zinc alloys were being produced and traded in the precise era and region that would have inspired Plato's tales. They may not be the legendary Orichalcum of Atlantis, but they are a snapshot of the material palette from which such a legend could have been drawn. The true mystery, then, may not be the base metal, but the exceptional properties the legend insists it possessed. Could an ancient alloy have achieved a particular acoustic resonance, making it prized for ceremonial gongs or instruments? Might a specific treatment or impurity have given it an unusual corrosion resistance, perfect for maritime applications on a seafaring empire like Atlantis? These are the questions that transition the search from historical curiosity to material science inspiration. If a distinct, high-performance copper-zinc alloy with unique traits did exist, its rediscovery could open new avenues. Modern engineers constantly seek specialized non-ferrous metals, alloys that do not rely on iron. For advanced electronics, we need materials with excellent electrical conductivity but greater durability and resistance to oxidation than pure copper. For marine hardware, from ship propellers to underwater sensor housings, we need metals that can withstand saltwater corrosion for decades without failing. A legendary alloy like Orichalcum, even just the idea of it, serves as a challenge, a proof of concept that such a material was once considered achievable. It pushes researchers to ask, what if we combine those base elements with a different process? or introduced a new mineral catalyst to create a modern alloy with that legendary blend of beauty, strength, and permanence. Ultimately, Orichalcum represents the most poetic form of loss. It is a material that may have been real, but whose identity is now inseparable from the story that carried it through time. This intertwining is itself a kind of material property, the ability of a substance to capture the human imagination so completely that its practical reality becomes secondary to its symbolic power. The quest for it is therefore a dual excavation, digging through both geological layers and narrative layers. We are not just looking for a metal, we are trying to separate the gleam of fact from the glow of legend. In doing so, we honor a profound human impulse to believe that the past held wonders that outshone our present, and that by recovering even their echo, we might forge a future with a little more of that lost brilliance. The story of a lost material is always at its heart a story of a broken connection. We have wandered through legends of unbreakable glass and self-healing concrete, of dyes that defied time and flames that defied the sea. Each disappearance feels like a unique tragedy, a singular thread snipped from the tapestry of progress. But when we step back, patterns emerge in the silence. These were not random acts of forgetting. They were the inevitable fractures in human systems, the predictable points where knowledge, no matter how brilliant, can slip through the cracks and vanish. Understanding why these materials were lost is not just an academic exercise. It is the key to ensuring our own discoveries do not one day become mysteries for a future age to ponder. The most dramatic catalyst is the collapse of a civilization itself. When an empire falls, it is not just political order that disintegrates. The intricate trade networks that supplied rare ores or exotic resins are severed. The centralized workshops where master artisans collaborated are abandoned. The economic stability that supported decades of research and apprenticeship evaporates. Specialized knowledge becomes a liability, a useless relic in a world now focused on survival. The recipe for a legendary alloy or a perfect mortar is not burned in a library fire. It is simply no longer taught because the society that needed it and the system that sustained its creators has ceased to exist. The knowledge fades not with a bang, but with a slow, generational whisper, until the last person who knew how to temper that particular steel or mix that specific glaze takes the secret to their resting place. Even within stable societies, knowledge was often guarded into oblivion. Craft guilds and artisan families operated on a principle of competitive secrecy. A unique formula for a vibrant ceramic glaze or a superior metal alloy was not intellectual property to be shared. It was the family fortune, the source of their prestige and livelihood. This protective instinct was rational, but it created a profound vulnerability. If a master died suddenly without passing the full secret to a worthy heir, or if a guild was dissolved by political decree, the knowledge chain was broken permanently. The technique was not documented, it was embodied. It lived in the feel of the clay at a certain temperature, in the exact color of the flame in the forge, in the rhythmic hammering passed from a teacher's hand to a student's arm. This is what scholars call tacit knowledge, understanding that is learned by doing and is incredibly difficult to translate into written words. When the doing stops, the knowledge evaporates like morning mist. Then there are the moments of catastrophic loss, the burning of libraries and repositories that haunt our historical imagination. The destruction of the Library of Alexandria is the most famous symbol, but it is just one example in a long, sad history. Centuries later, the House of Wisdom in Baghdad, a beacon of scholarship and translation, was similarly devastated. These were not just buildings full of scrolls. They were the collective hard drives of their age, where observations from India, Greece, Persia, and beyond were compiled, compared, and built upon. When such a center is lost, it is not a single book that disappears. It is the conversation itself that is silenced. A fragmentary mention of a flexible glass in one text might have been explained by a detailed treatise in another, now ash. The connections that spark innovation are severed, and progress must start again from the remaining fragments, unaware of how much further the previous generation had already reached. And sometimes the thread is cut by deliberate human hand. The legend of Tiberius and the unbreakable glass points to a chilling possibility: the active suppression of a technology. An authority, whether an emperor fearing the devaluation of gold or a religious body fearing social change, can see a new material not as progress, but as a threat to the existing order. This moves the loss from the realm of accident to the realm of choice. It represents a road not taken because a gate was deliberately closed and locked. Innovation in such an environment does not merely slow down, it is steered away from entire avenues of possibility, leaving us to wonder what other transformative ideas have been stifled at their birth by short-sighted fear or the desire to maintain control. So what does this pattern of loss tell us about our own world? We live in an age of digital abundance where it feels like every piece of information is forever backed up on a cloud server. But the vulnerability has shifted, not vanished. Our knowledge is now concentrated in digital formats and storage media that may become unreadable to future generations, a high-tech version of a scroll in a forgotten language. Critical expertise in fields like advanced chip fabrication or spacecraft design can still reside in the tacit knowledge of a retiring generation of engineers. And the suppression of innovation can take subtler forms through funding biases, publication gatekeeping, or the abandonment of promising research lines that do not promise immediate profit. The legacy of these lost materials, therefore, is an urgent lesson in stewardship. It teaches us that preserving progress requires more than just recording facts in a book or a database. It requires maintaining the living ecosystems of innovation, the schools, the apprenticeships, the open exchanges of ideas, and the cultural value placed on curiosity for its own sake. It asks us to be archivists of not just information, but of the human context that makes that information meaningful. By studying why these ancient wonders disappeared, we are not just solving historical puzzles. We are learning how to build a future where our greatest discoveries are not one day reduced to legends, but remain active, evolving conversations, lighting the way forward for all the generations to come. These vanished substances leave no eyewitnesses, only silent evidence. To interrogate that evidence, modern science has assembled a detective toolkit of almost magical precision, turning each recovered artifact into a silent witness that can be made to speak. The investigation begins not with a hypothesis, but with a deep, non-invasive observation. Before a single grain of material is disturbed, researchers might use advanced imaging techniques like computed tomography or CT scanning to peer inside a corroded lump of metal or a sealed ceramic vessel. This digital archaeology reveals hidden structures, internal flaws, or even traces of what the container once held, all without ever touching the original object. It is the equivalent of giving history an X-ray. Once the internal landscape is mapped, the real forensic work begins at the microscopic and even atomic level. This is where tools like the scanning electron microscope, or SEM, and the transmission electron microscope, or TEM, become indispensable. Remember the swirling pattern on Damascus steel. These powerful microscopes were the key to solving that mystery. By firing a beam of electrons at a carefully prepared sample, they can produce images magnified hundreds of thousands of times, revealing a world invisible to the ancients. It was under the gaze of a TEM that researchers discovered the carbon nanotubes within the steel, the nanostructures that gave the blade its legendary properties. This is not merely looking closely, it is seeing an entirely different dimension of the material, a dimension where its true secrets are written, but knowing the structure is only half the story. To understand the recipe, you must know the ingredients. This is where chemical analysis enters the lab. Techniques like X-ray diffraction bombards a sample with X-rays and analyzes how they scatter. Each crystalline material scatters the rays in a unique pattern, like a fingerprint. This allows scientists to identify the specific minerals present, whether it is the self-healing aluminous tobamorite in Roman concrete or the particular blend of copper and zinc in a suspected Orichalcum ingot. Meanwhile, spectroscopy, which studies how matter interacts with light or other energy, can detect the precise chemical elements and even their molecular bonds. A laser directed at a fleck of ancient pigment can reveal not just that it contains mercury, confirming it is cinnabar, but also how that mercury is bonded to sulfur, telling us about the purity and processing of the original ore. These tools move the investigation from the realm of observation into the realm of reverse engineering. Yet for all this analytical power, some questions can only be answered by getting your hands dirty, quite literally. This is the domain of experimental archaeology, a field dedicated to reconstructing the past through practical action. Archaeometallurgists, for example, will build a replica of an ancient furnace based on archaeological finds, using period-appropriate materials like clay and stone. They will then attempt to smelt ore using charcoal and bellows, meticulously recording temperatures, airflow, and the resulting metal. Each failed attempt is not a setback, but a data point, ruling out one possibility and narrowing the path toward the method that actually works. This process breathes life back into silent ruins, transforming a pile of slag and a furnace base into a functioning workshop where the past is actively, noisily tested. Finally, when physical clues are scarcest, science turns to the digital realm. Computational chemists can now create sophisticated models of potential reactions. If an ancient text mentions mixing 3 substances but gives no proportions, researchers can simulate thousands of combinations in a virtual environment, predicting which ones would yield a stable, useful material. This digital alchemy provides a roadmap for the physical experiments, guiding them toward the most promising avenues and saving invaluable time and resources. This entire process represents a profound shift in how we engage with history. It is an interdisciplinary marriage, a constant dialogue between the historian translating a cryptic text, the archaeologist carefully unearthing a workshop site, and the materials scientist analyzing a fragment with $1 million microscope. Each specialist speaks a different language, but they are united by a single question: how was this done? The lost recipe is no longer a ghost. It is a fragmented blueprint, and each of these tools is a way to find another piece, to connect another line, until the outline of a forgotten genius begins to emerge once more from the shadows of time. The breakthrough in understanding Damascus steel did not come from a forge, but from a laboratory. For generations, skilled bladesmiths had tried in vain to recreate the legendary metal, focusing obsessively on replicating its beautiful, watery surface pattern. They would fold and weld different grades of steel, a technique known as pattern welding, which produced a stunning visual mimic. Yet these new blades, while often excellent weapons in their own right, lacked the supernatural combination of flexibility and razor sharpness described in the ancient texts. The craftsmen were chasing a ghost because they were trying to copy the effect without understanding the cause. They were solving the wrong puzzle. The true turning point arrived when researchers stopped asking how to make the pattern and started asking what the original metal actually was. Using transmission electron microscopes, they peered into samples of authentic antique blades at a scale unimaginable to the original smiths. There, they found the astonishing secret, a forest of carbon nanotubes and nanowires woven into the steel's matrix. This was not a matter of artistic folding, it was a feat of nanoscale engineering achieved over 1,000 years ago. The discovery immediately redirected the search. If these structures were the source of the legendary properties, then how were they formed? the investigation pointed to two interdependent factors: the recipe and the process. The source material was identified as a specific type of high-carbon steel ingot known as woots, which originated in India. Crucially, this ore contained unique trace impurities, elements like vanadium, which likely acted as catalysts during the forging process, helping to guide the formation of those microscopic reinforcing structures. The second factor was the meticulous, rhythmic thermal cycling. The master smith would heat, hammer, and cool the metal in a precise, repeated sequence, perhaps over many days. This was not random pounding. It was a carefully controlled dance of temperature that encouraged the carbon in the steel to precipitate out and arrange itself into those miraculous nanotubes. The smith was essentially programming the metal's internal architecture through heat and timing, guided by generations of accumulated, tacit knowledge. Today, a perfect, one-to-one historical replica of the original process remains just beyond our grasp. We understand the destination, but the exact path the ancients walked, the feel of the hammer and the color of the heat, is still partially obscured. Yet this partial rediscovery is far from a failure. It is a resounding success that has fertilized entire new fields of research. Modern metallurgists, inspired by the principles of Damascus steel, have developed incredibly sophisticated pattern-welded composites and are experimenting with controlled processes to introduce nanostructures into modern alloys. The goal is no longer to make a historical curio, but to harness that ancient wisdom for contemporary challenges, creating stronger, lighter, and more resilient materials for everything from medical implants to aerospace components. The journey to understand this lost material demonstrates a profound truth. The value of the quest often outweighs the value of the prize. By striving to answer a historical question, we did not simply recover an old recipe, we unlocked a new way of seeing material science itself. The ghost of Damascus steel continues to guide us, not back to the past, but forward into a future built on the forgotten genius of those who came before. The laboratory can recreate a flame, but not the legend. Our modern detective work hits a formidable wall with the case of Greek fire, a substance whose true nature remains frustratingly out of reach, illustrating the stark limits of even our most advanced reverse engineering. While we can confidently list its probable ingredients, crude petroleum, quicklime, sulfur, and perhaps saltpeter, this is akin to knowing flour, water, and yeast are used in bread without knowing the exact proportions, the kneading technique, or the baking temperature. The precise formula, the exact viscosity that allowed it to be projected in a continuous stream, the chemical trigger for its ignition, and the engineering of its pressurized delivery system, these details are still fiercely debated by historians and chemists. Experimental recreations based on historical descriptions produce impressive, flammable liquids, but none have yet matched the legendary, almost supernatural intensity and its defining, terrifying trait, a fierce resistance to being doused by water. These modern attempts burn, but they do not dance across the waves with the same malevolent life described by panicked medieval sailors. This gap highlights a key obstacle in our search for lost materials, the nature of historical evidence itself. The accounts we rely on were written by observers, not chemists, often using metaphorical and awe-struck language. They describe a liquid fire that clung to ships and water alike, but they do not provide a technical manual with measurements and chemical equations. The loss is therefore more profound and complete, residing not in a missing scroll, but in the tacit, hands-on knowledge of the Byzantine engineers who worked in those secretive imperial workshops. This knowledge lived in the feel of the mixture's thickness, the sight of a specific bubble pattern during heating, the sound of the pump's mechanism, and the rhythmic procedure passed from master to apprentice through demonstration alone. That chain of embodied skill was broken forever when Constantinople fell. This case teaches a necessary humility. It shows that some secrets, forged in the crucible of conflict and protected with absolute severity, may remain permanently locked away by the passage of time. The puzzle of Greek fire reminds us that not all mysteries of the past are meant to be solved, and that some doors once closed cannot be reopened. This acceptance is not a failure of science, but a recognition of history's depth and the fragile, human dimension of technological mastery. Some echoes fade until only silence remains, a quiet lesson in the irretrievable cost of loss. The most transformative materials may have been the most fragile. While stone and metal endure in ruins, whispering their secrets across millennia, the true technological soul of many ancient societies was woven, glued, and preserved from the living world. We have likely lost a vast library of organic and composite innovations, substances crafted from plants, trees, animal products, and ingenious combinations that decomposed long ago, leaving only faint chemical echoes. Our historical gaze is naturally drawn to the glitter of gold and the solidity of marble, but the everyday genius of the past might have been a waterproof cloak, an unbreakable wooden joint, or a ship's hull that resisted rot for a century. These materials represent a different kind of mystery, one where the evidence has mostly returned to the earth. Consider the ancient shipwright. Historical accounts from cultures like the Romans or the Vikings speak of voyages lasting years and ships that served for generations, a lifespan that seems impossible for wood constantly assaulted by seawater, microbes, and burrowing worms. They undoubtedly employed sophisticated treatments, brews of tar, resins, oils, and perhaps even plant extracts with natural biocidal properties. The exact recipes, the specific combinations and application methods that yielded such legendary durability are largely lost to us. We find ships preserved in unique, oxygen-deprived mud like the Viking longships, but the original protective coating has often washed away, leaving only the bare, miraculously surviving wood. The secret is not in the timber itself, but in the vanished chemistry that shielded it. This search extends to the very glue that held civilizations together. The artisans who constructed the legendary composite bows of the steppe nomads, weapons of incredible power and resilience, used animal glues and sinews applied in specific, tension-bearing layers. The exact formulation and curing process created a material that was far stronger than the sum of its parts. Similarly, the binders used in ancient paints, like those in Egyptian tombs or Renaissance frescoes, often involved complex organic mixtures, egg tempera or plant gums, that gave the pigments their luminosity and astonishing longevity, outlasting modern acrylics by centuries. Even in construction, mortars sometimes included organic additives like animal blood, beer, or fruit extracts to improve workability, bonding, or water resistance, a form of intuitive chemistry we are only beginning to appreciate through residue analysis. Because these materials decay, the detective work becomes supremely delicate. Scientists are not looking for a tool, but for its ghost. They use techniques like gas chromatography to analyze the microscopic residues inside a clay pot, identifying the faint chemical signature of a fermented beverage, a medicinal oil, or a resinous adhesive. They study the exceptional preservation offered by extreme environments, like the acidic peat bogs that tanned and preserved leather goods for thousands of years, or the icy tomb that safeguarded Ötzi the Iceman and his gear. His copper axe was mounted with a handle using an advanced adhesive, a mix of birch tar and beeswax, demonstrating a sophisticated understanding of composite materials over 5,000 years ago. Each of these clues is a fragment of a much larger, mostly missing manual on ancient organic engineering. The potential rewards for recovering this knowledge are immense and strikingly modern. In an era grappling with plastic pollution and toxic industrial processes, ancient organic chemistry offers a vision of sustainable, circular material science. Imagine rediscovering a plant-based polymer, a biodegradable material with the versatility of plastic, but designed to safely return to the ecosystem. Envision non-toxic, highly effective wood preservatives derived from natural compounds, replacing the chemical treatments we use today. Consider powerful, waterproof textile finishes made from renewable resources, or super-strong bio-adhesives for construction and manufacturing that leave no harmful footprint. This is not a retreat to primitivism, but a forward-looking partnership with the past. The ancient artisans were masterful green chemists by necessity, working within the limits and bounty of their natural environment. They developed solutions that were effective, locally sourced, and ultimately compatible with the world around them. By learning to read the faint chemical poems they left behind in residue and ritual, we are not just uncovering lost arts. We are finding potential blueprints for a more sustainable future, written in the forgotten language of leaves, resins, and roots. The quest to recover lost knowledge is not a simple race against time. It is a negotiation with the future we wish to build. Every time we stand on the verge of resurrecting a forgotten power, we must pause and ask a critical question, should we? The principle is known as dual use, where a single technology can be a tool for profound good or immense harm, and it applies with piercing clarity to the materials of the past. Consider the stark example of Greek fire. To recover its formula would be a monumental historical and chemical achievement, but its primary purpose was unambiguous, a weapon of terror and destruction. Introducing such a potent incendiary agent into the modern world, with its own existing arsenals and conflicts, could have unpredictable and dangerous consequences. The same analytical techniques that might unlock a self-healing concrete could also be directed toward creating more resilient, hazardous materials. The power is neutral, but human intention is not, and we must honestly assess our capacity to wield rediscovered forces responsibly. This ethical dimension extends beyond weapons into the realm of ancient well-being. Historical texts sometimes describe remedies involving substances we now know to be toxic, like certain heavy metals or powerful psychoactive plants. A literal, uncritical recreation could cause serious harm, missing the nuanced context in which ancient healers might have used minute doses or complex antidotes. There are even fringe theories, though widely disputed, that speculate about ancient awareness of radioactive materials. While these remain in the realm of legend, they underscore the broader point: not all lost knowledge is safe knowledge, and our enthusiasm for discovery must be tempered by rigorous safety and ethical review. The concern is not only physical but cultural. Many of the world's most sophisticated pharmacopoeias and material traditions belong to indigenous and local communities, held as sacred, living knowledge. The act of extraction, of taking a plant compound or a weaving technique and isolating it for commercial profit without consent or benefit sharing, is a form of modern exploitation. It commodifies a cultural heritage, often distorting its original meaning and severing it from the spiritual and communal context that gave it purpose. Rediscovery in these cases is not a neutral archaeological act. It is an intervention into a living system of knowledge. Therefore, a responsible path forward cannot be walked by scientists and engineers alone. It requires a council of perspectives. Ethicists must help frame the questions of intent and potential misuse. Historians and cultural anthropologists must provide the crucial context to understand a material's original role and significance. Most importantly, the voices of descendant communities must be centered and heard, ensuring they are partners in the process, not merely subjects of study. This collaborative, deliberate approach slows the race to the lab, but it enriches the journey. It ensures that if we are to bring a piece of the past back into the light, we do so with our eyes wide open, considering not only if we can, but why we should and for whom. The legacy of a lost material is not just its chemical formula, it is the wisdom with which we choose to welcome it home. A single rediscovery could rewrite the global economy in a generation. The sudden recovery of a material like Starlight or the complete formula for Roman concrete would not merely be a headline for scientific journals. It would trigger a cascade of industrial transformations, reshaping markets, redefining costs, and redrawing the map of global advantage. The initial shockwave would be felt in the most foundational sectors, construction and infrastructure, which consume vast portions of national budgets, would undergo a revolution. Imagine roads, bridges, and seawalls engineered with self-healing concrete, structures that actively repair stress cracks and resist corrosion for centuries instead of decades. The immediate cost would be immense, but the long-term savings would be measured in trillions, freed from the endless cycle of inspection, maintenance, and replacement. This capital could then flow into new projects, education, or healthcare, fundamentally altering public investment for generations. The energy sector would face a similar upheaval. A perfect, scalable thermal insulator like Starlight, capable of withstanding extreme temperatures, would redefine efficiency. Power plants could operate at higher efficiencies with less waste heat. Buildings could become virtually passive, requiring minimal energy for heating or cooling. The transportation of liquefied natural gas or the containment of fusion reactor plasmas could become far safer and more economical. Consumer electronics, from smartphones to laptops, could shed bulky cooling systems, allowing for sleeker designs and longer battery life as energy is conserved, not dissipated as heat. In aerospace, new superalloys inspired by lost metallurgies could lead to lighter, stronger airframes that consume less fuel, make travel safer, and significantly reduce operational costs for airlines, potentially making global connectivity more affordable. Yet for every industry reborn, another might face obsolescence. This is the dual edge of disruptive innovation. Entire sectors built on manufacturing, selling, and installing current-generation materials, from certain specialty chemicals and coatings to conventional steel and cement production, could find their products suddenly inferior and their business models collapsing. The economic displacement would be real, impacting supply chains, employment, and communities built around those technologies. The rediscovery is not just a gift, it is a test of our foresight and our values. It forces difficult questions about transition. How do we manage the shift to protect workers and regions whose livelihoods are tied to the old ways? Can we develop retraining programs and economic buffers to ease the transformation, turning potential loss into an opportunity for skilled renewal? Furthermore, the question of ownership looms large. Who holds the intellectual property rights to a recipe inspired by a 2,000-year-old Roman text or a concept demonstrated by a lone inventor? Would this knowledge be patented by a corporation, locked behind a paywall that could limit its life-saving or planet-saving applications? Or could it be managed as a global public good, with licensing frameworks designed to ensure equitable access and affordability for developing nations? The stakes could not be higher. A material that makes desalination plants last longer or creates ultra-efficient solar panels must not become a tool for exacerbating global inequality, but a bridge toward closing it. Ultimately, the economic impact of a major rediscovery teaches us that innovation is never isolated in a lab. It ripples through the fabric of society, challenging our institutions, our economies, and our ethical frameworks as much as our scientific understanding. The true measure of our readiness for such a discovery may not be in our analytical instruments, but in our ability to steward its benefits with wisdom, ensuring that a miracle from the past builds a more equitable and resilient future for all. These historical mysteries do more than satisfy our curiosity. They actively shape the laboratories of tomorrow. Even when a complete recipe remains frustratingly out of reach, the simple, verified existence of these ancient materials serves as one of the most powerful catalysts for modern innovation. They are not dead ends, but rather signposts pointing toward realms of possibility we had not yet fully mapped. This is the concept of an existence proof, a demonstration that a certain feat is not only imaginable but has already been physically achieved. For a researcher facing skepticism or a theoretical dead end, there is no more compelling argument than being able to point to a 2,000-year-old artifact and say, "Look, it has been done before." The quest for Damascus steel provides the perfect example. For decades, the idea of a metal that was both incredibly hard and shockingly flexible seemed to push against the known limits of metallurgy. But the discovery of carbon nanotubes within those ancient blades changed the entire conversation. It was not a theory anymore, it was a fact. This historical proof directly inspired and accelerated contemporary research into carbon nanotube-reinforced metals, giving scientists a clear, historical benchmark to strive for and surpass. It redirected entire research programs, providing a tangible goal that was no longer speculative, but validated by history itself. Similarly, the Lycurgus cup is not merely a museum piece. It is a foundational case study in the modern field of plasmonics, which explores how light interacts with nanostructures. Before its secrets were uncovered, manipulating light at the nanoscale was a theoretical frontier. The cup proved that such manipulation was not only possible, but could be achieved through chemical means without billion-dollar clean rooms. It fuels ongoing research into nanoparticle applications for medical diagnostics, ultra-efficient solar cells, and smart materials that change properties on demand. These ancient artifacts encourage a radical form of creative thinking in modern labs. They push scientists to step outside the conventional parameter space defined by current textbooks and industrial processes. When you know a medieval smith created nanostructures with a charcoal forge, you are forced to reconsider the absolute necessity of your high-tech, energy-intensive equipment. It prompts questions like, what if we try a slower cooling cycle? What if we introduce this trace mineral as a catalyst? What if the secret is not in a purer material, but in a specific, controlled impurity? History, in this light, becomes the most imaginative research and development department one could hope for. It presents solutions that are elegant, often sustainable, and born from a deep, intuitive dialogue with natural processes. These lost materials challenge the very timeline of progress, suggesting that the next great leap forward might not always be found by inventing something entirely new, but by recovering a forgotten principle and viewing it with modern understanding. They teach us that innovation is not a linear march, but a spiral where we sometimes circle back to a point of profound insight that was reached long ago, waiting for us to arrive with the right tools to see it clearly and continue the journey. The next great library we must search may not be made of stone, but of code. As we stand amid the fragments of the past, a new partner joins the quest, one that thinks in patterns we cannot perceive. Artificial intelligence and machine learning are emerging not as replacements for human curiosity, but as its most powerful amplifiers, turning the search for lost materials into a digital detective story of unprecedented scale. Imagine every surviving scroll, ledger, and technical manual from antiquity painstakingly digitized. A human scholar can spend a lifetime mastering a single language and corpus. An AI, however, can be trained to read them all at once in dozens of ancient languages, scanning for subtle clues. It is not looking for a single word like Orichalcum. It is searching for constellations of terms, patterns of description that escape our linear reading. A mention of a metal that rings like a bell in one text, coupled with a reference to a mine near a specific river in another, and a record of its trade value in a third. These disconnected data points scattered across centuries and continents can be linked by machine learning algorithms, highlighting potential leads for historians to investigate with a focus no human team could sustain. Beyond texts, the true power of this digital archaeology lies in simulation. We now possess vast databases of material properties, the chemical behaviors of elements and compounds under different conditions. Machine learning models can ingest this modern knowledge alongside fragmented historical data, the known ingredients of an era, and the described properties of a lost substance. Then they can simulate millions, even billions of potential chemical combinations and manufacturing processes in a virtual space, searching for recipes that would yield the legendary effects we read about. It is a form of computational alchemy, testing possibilities at a speed that would take human researchers thousands of lifetimes. These models do not give definitive answers. They generate high-probability suggestions, plausible blueprints for the physical world. A list of 5 most likely alloy compositions for a flexible ancient glass, or a simulated thermal cycle for forging a steel with a specific nanostructure. These become targeted hypotheses for a laboratory to test, transforming a needle in a haystack search into a guided expedition. This digital toolkit extends into the very workshop. 3-dimensional modeling and physics simulations allow researchers to virtually reconstruct ancient manufacturing sites. Using archaeological data, they can build a digital twin of a Roman concrete mixing yard or a medieval smithy. They can simulate the flow of air through a furnace, the heat gradients in a crucible, or the stresses on a loom. This virtual experimentation helps answer practical questions that texts never address. How many workers were needed to maintain the temperature for a week-long process? What was the most efficient arrangement of bellows and vents to achieve a consistent heat? By virtually testing these parameters, we gain insights into the tacit knowledge, the embodied skills that were never written down. This creates a powerful, accelerating feedback loop. Data from a real artifact, like the precise elemental makeup of a pottery shard analyzed by a spectrometer, is fed into the AI model. The model refines its simulations and suggests a new, more accurate historical context or recipe variation. That new hypothesis then guides the next physical experiment, perhaps an attempt to recreate the pottery glaze using the suggested method. Each cycle, digital to physical and back again, sharpens our understanding, closing in on the lost truth with exponential efficiency. This partnership reshapes the entire endeavor. The historian provides the question and the cultural context. The AI provides the pattern recognition and brute force computation. The material scientist provides the laboratory for validation. Together, they form a trinity for time travel, not in a fantastical sense, but in the very real sense of reconstructing a thought process, a solution, a moment of genius that the world had long ago set aside. The future of rediscovery is here, and it speaks the language of data, offering a whispered promise that some of our oldest mysteries may finally be solved by our newest machines. The most brilliant discoveries often begin with an accident. The careful, methodical work of major universities and national laboratories represents one vital path to rediscovery, but history whispers that another, equally important route is far less predictable. It is paved with chance encounters, stubborn curiosity, and the quiet dedication of those who pursue knowledge for its own sake. The story of the Antikythera Mechanism, that ancient astronomical computer, did not start in a museum archive. It began with a team of sponge divers in 1901, seeking shelter from a storm off the coast of a Greek island. What they hauled up from the seafloor was not just a shipwreck, but a time capsule containing a technological ghost that would redefine our understanding of ancient science. That pivotal moment was pure serendipity, a lucky break that placed a corroded lump of history into the hands of humanity. It reminds us that the past does not always reveal itself on a planned excavation. Sometimes it washes ashore after a storm, or lies waiting in a forgotten attic, or is spotted by an eagle-eyed amateur in a field, this pattern extends beyond the initial find to the very process of interpretation. Formal academic research provides the essential framework, the peer review, and the advanced instrumentation. Yet, key insights often spark from unexpected places, from minds working outside traditional corridors. Consider the historical blacksmith who spends weekends in a backyard forge, attempting to recreate the folding patterns of a Viking sword using period-accurate tools. His hands-on experience with the feel of hot iron, the sound of a proper strike, and the color of the metal at critical temperatures generates a form of tacit knowledge that a textbook cannot convey. This practical wisdom can solve puzzles that pure theory cannot, offering plausible explanations for how ancient artisans achieved their results with the tools they had. Similarly, a chemist tinkering in a home garage, cross-referencing a formula from an alchemical text with a modern database of reactions, might stumble upon a combination that a large, grant-funded lab focused on more conventional approaches would never think to test. These independent researchers operate without institutional constraints, free to follow whims and hunches down rabbit holes that a formal project proposal might deem too speculative. The cautionary tale of Maurice Ward and Starlight embodies both the immense potential and the profound frustration of this solitary path. Ward was not a materials scientist with a doctorate. He was a hairdresser and an inveterate tinkerer whose revolutionary insulating putty was born from experimentation in his own workshop. His demonstration was undeniable, capturing the imagination of the world. Yet, his deep-seated secrecy and distrust of large institutions ultimately prevented that breakthrough from being validated, scaled, and shared. Here, the brilliant amateur, unburdened by conventional thinking, made the discovery, but the lack of a bridge to the collaborative, open world of science meant the discovery could not fully serve humanity. This story underscores a critical lesson, not that amateur work is flawed, but that its greatest value is realized when it connects to broader ecosystems of knowledge. This highlights an urgent need for open channels between formal science and the vibrant world of citizen research. Online platforms now allow enthusiasts to transcribe ancient weather logs, classify galaxy shapes, or model protein folds, contributing to real scientific progress from their living rooms. Museums and universities are increasingly creating programs to engage with independent scholars, historical reenactors, and artisan practitioners, recognizing that their hands-on expertise and alternative perspectives are invaluable. The goal is to build a more porous, inclusive network of discovery, where a curious individual with a unique insight can find a pathway to share it with experts who have the tools to explore it further. The next pivotal clue that unlocks a lost material might not come from a lab with a multi-million-dollar grant. It could emerge from a gardener who notices a peculiar reaction between a clay soil and a specific plant ash, from a painter experimenting with historical pigments, or from a novelist who, while researching for a book, spots a tantalizing connection between two obscure texts. Curiosity is the most universal and powerful research tool we possess. By fostering environments where diverse kinds of curiosity can meet and collaborate, we do not just increase our chances of finding what was lost. We honor the very spirit of inquiry that drove the original creators, ensuring that no future genius in any garage or workshop ever has to keep their light under a bushel. Our own laboratories now create wonders that would seem like magic to the past. We engineer metamaterials that bend light in impossible ways, craft graphene composites stronger than diamond, and grow bioengineered tissues that could one day repair human hearts. These are the crown jewels of our scientific age, materials poised to redefine medicine, energy, and technology. Yet the ghosts of Damascus steel and Greek fire whisper a sobering warning from across the centuries. Without deliberate care, our most advanced creations could suffer the same fate, becoming the indecipherable legends of a future era. The question is no longer just how to recover lost knowledge, but how to actively preserve the knowledge we are creating right now to ensure it survives the inevitable tests of time, disaster, and societal change. The first, most critical step is a cultural shift in how we document discovery. For too long, scientific progress has been communicated in a final, polished form, the published paper. This document often omits the messy, vital reality of the process, the failed experiments, the subtle adjustments, the exact feel of the material at a specific temperature that made the difference between success and failure. To future researchers, these omitted details are the recipe itself. We must move toward a new standard of open access, not just for results, but for the entire experimental journey. This means detailed, standardized logs that capture every variable, every piece of raw data, and crucially, video recordings of procedures that convey the tacit knowledge, the rhythm and technique that a written description cannot. Imagine a future scientist 500 years from now accessing not just a paper on a revolutionary polymer, but a digital archive containing the lab notebook entries, the spectrometer readouts from every trial, and high-definition video of the precise stirring motion required during synthesis. This level of documentation transforms a static fact into a reproducible craft. Preservation, however, is meaningless without a durable vessel. Our reliance on digital storage presents a unique and ironic vulnerability. The hard drives, servers, and cloud platforms we trust today are far more fragile over centuries than clay tablets or parchment. File formats become obsolete, storage media degrades, and the very energy systems required to maintain vast data centers are not guaranteed across millennia. The solution must be one of radical redundancy, storing identical copies of our scientific heritage in multiple, geographically dispersed formats, from hardened digital archives to analog backups like micro-etchings on durable metal plates, designed to be readable with simple magnification. We must think like archivists for the ages, building a library of Alexandria for the digital era with the explicit goal of outlasting civilizations. Finally, and most importantly, we must preserve the human chain of understanding. The deepest knowledge of a material, its quirks and potentials, often lives in the minds and hands of the researchers and engineers who work with it daily. This is the modern equivalent of the master smith's tacit skill. We cannot let this expertise retire or fade away. It requires intentional mentorship programs, the creation of living repositories of skill where seasoned practitioners actively teach the next generation, passing on not just the what, but the how and the why. Universities and industries must value and fund this transmission of craft as highly as they value new breakthroughs. The legacy we choose to leave is now ours to design. By learning from the fragmented whispers of history, we have a profound duty and a rare opportunity. We can build a knowledge ecosystem that is resilient, transparent, and radically accessible. This is not about hoarding information, but about gifting it forward, creating a foundation so solid that the progress of our age does not become a series of tantalizing, unsolved mysteries for our descendants. It is about ensuring that the light we are casting today continues to illuminate the path for all who follow, turning our present marvels into permanent pillars for humanity's endless journey of discovery. A single artifact can belong to the world, but its story belongs to a people. The search for lost materials is no longer a solitary treasure hunt led by distant institutions. It has evolved into a global conversation, a delicate and necessary partnership that bridges modern laboratories with the ancient lands where these mysteries were first born. True discovery now requires more than advanced spectrometers. It demands deep respect, mutual trust, and a fundamental shift from a narrative of extraction to one of shared stewardship. This means the work to understand Damascus steel is conducted in collaboration with metallurgists and historians in India and Iran, where the Wootz ingots originated. The study of Roman concrete is a joint venture with Italian and Greek researchers who are the direct inheritors of that architectural legacy. The decoding of ancient Chinese metallurgical texts or the analysis of pre-Columbian alloys happens through partnerships with scholars and institutions within those nations. This collaborative model ensures that knowledge is not taken but co-created. It guarantees that artifacts can be studied using non-invasive, portable technologies, often without ever leaving their countries of origin, preserving their physical and cultural context. The benefits of this approach ripple outward in profound ways. For the international scientific community, it provides access to deeper, more nuanced understanding that only local expertise and cultural insight can provide. A historian from Rome can explain not just how a concrete mix was used, but why it was chosen for a particular temple, infusing the chemical data with layers of meaning. For the host nations, these partnerships build local scientific capacity, train a new generation of experts in archaeometry, and reinforce the incredible value of their own cultural heritage. It transforms historical sites and museum collections from static displays into active, living centers of research and innovation. This shared journey also directly confronts a painful legacy. For centuries, priceless artifacts were removed from their homelands, often under colonial contexts, severing them from the stories that gave them life. Modern collaborative science offers a path to redress this, not by moving objects but by moving knowledge. A scanner can travel to a museum in Cairo, a research team can be invited to a workshop in Damascus, and the data, the most valuable commodity, can be shared instantly across the globe. The goal is to ensure that the communities who are the custodians of this heritage are the primary authors and beneficiaries of its rediscovery. When a breakthrough is made about a legendary Incan metalworking technique, it should first and foremost enrich the educational and cultural institutions of the Andes. When a forgotten die is recreated, the artisans from the region where it was first perfected should have a voice in how that knowledge is applied and shared. This ethical framework does not slow down science, it enriches it with legitimacy and depth. It recognizes that the recipe for a lost material is not just a list of ingredients, it is a chapter in a people's story, a testament to their ancestors' ingenuity. By honoring that story, we do more than recover a chemical formula, we rebuild bridges of respect and understanding. We make the past a common ground, not a contested site. In the end, the greatest material we might rediscover through this cooperative spirit is not a metal or a glass, but something far more durable, a shared sense of wonder and a collective commitment to preserving the brilliant, fragile tapestry of human achievement for every generation to come. The true legacy of these lost materials is not a simple list of what we have misplaced. It is a mirror reflecting both the breathtaking heights of human creativity and the sobering ease with which our greatest achievements can vanish into silence. Each of these substances, from the nano-forged blades of Damascus to the self-healing concrete of Rome, stands as a monument to a moment when our ancestors solved a problem with such elegance that we still struggle to follow their path. They are proof that progress is not a straight, upward line, but a winding road with forgotten peaks we must sometimes climb again. These ancient solutions offer us more than historical intrigue. They hold priceless clues for building a more sustainable and advanced future. The self-repairing nature of Roman concrete inspires our quest for resilient infrastructure. The enduring color of Tyrian purple guides our search for stable, organic chemistry. The principles hidden in these artifacts are not obsolete. They are simply awaiting our modern understanding to unlock their full potential. While some secrets, like the exact alchemy of Greek fire, may remain forever entombed by time and conflict, the very act of searching for them has already transformed our world. This ongoing detective work, powered by electron microscopes and artificial intelligence, continually expands the boundaries of material science. It forces us to think creatively, to question our assumptions, and to see collaboration across disciplines and cultures not as a luxury, but as the essential engine of rediscovery. As we stand on the shoulders of these ancient giants, we have a profound responsibility. We must continue the investigation with both our most cutting-edge tools and a sense of humble curiosity, recognizing that the past still has much to teach us. Equally, we must become better stewards of our own era's breakthroughs, documenting and preserving our knowledge with a care that honors those who came before. We must remain open to the possibility that the next great leap forward might not be found by inventing something entirely new, but by finally understanding a forgotten recipe, patiently waiting in a scroll, a shipwreck, or a legend, ready to illuminate our path once more. If this journey through lost knowledge has sparked your curiosity, we would love to hear your thoughts. Which of these legendary materials would you most want to see rediscovered in our time? Share your choice in the comments below and subscribe for more deep dives into the mysteries that shape our world. The silence left by vanished civilizations may hold their most profound secrets. We have traced the ghosts of materials we know were lost, but a far more tantalizing frontier remains: the substances we have no record of whatsoever. Our historical narrative is written by the survivors, by cultures that left behind libraries, ledgers, or enduring stone. Yet countless human societies flourished and faded without a written language, or their records were inscribed on materials like bark, cloth, or wood that returned to the earth long ago. Their technological brilliance, their material innovations, are silent chapters in our collective story. What did the architects of Göbekli Tepe, who carved and raised massive stone pillars over 11,000 years ago, know about manipulating their environment that we have not yet grasped? Their monument predates pottery and metallurgy as we define them, suggesting a sophisticated understanding of stone, leverage, and social organization. But what other materials might they have mastered that left no trace? The great cities of the Indus Valley civilization, like Mohenjo-Daro, showcase astonishing urban planning and standardized brickwork, yet their script remains undeciphered. Within those unread symbols could lie formulas for advanced ceramics, waterproof sealants, or metal alloys that vanished with their city's decline. Across the Americas and Africa, prehistoric cultures developed profound knowledge of their local ecologies. They created paints and dyes from minerals and plants, adhesives from tree saps and animal products, and building techniques perfectly adapted to their climates. These were not primitive experiments, but highly evolved material sciences, passed down through generations as oral tradition and practical demonstration. When those cultural chains were broken through conflict, environmental change, or the arrival of new populations, that entire library of practical chemistry and physics dissolved. We might find shards of their pottery or fragments of their tools, but the living knowledge of how to select the specific clay from that one riverbank, mix it with precisely this crushed shell, and fire it in a pit with that type of wood to achieve a perfectly waterproof vessel, that recipe is gone forever. It is a loss on a staggering scale, the erasure of countless paths of human ingenuity. This realization transforms the past from a museum of known artifacts into a landscape of infinite possibility. It means the most transformative material we could ever rediscover might not be mentioned in any surviving text. It might be waiting in plain sight, in an artifact we have already found but do not yet have the tools to fully understand. A simple-looking bead in a museum case might, under a future analytical technology, reveal a polymer coating or a nanostructure we cannot currently detect. A patch of discolored soil at an archaeological site might be the only chemical ghost of a legendary plant-based fiber, a fabric lighter and stronger than silk, whose cultivation and weaving technique are now utterly forgotten. This is why the field of archaeometry, the scientific analysis of archaeological materials, is so vital and so exciting. Each new analytical instrument is like a new language learned, allowing us to interrogate the silent artifacts with more penetrating questions. What we can learn from a speck of residue today would have been pure magic a century ago, and the tools of the next century will undoubtedly reveal layers of complexity we cannot currently conceive. So this exploration does not truly end. It simply pauses at the edge of the known. The legacy of lost materials is ultimately a story about the future, not the past. It is a reminder that human creativity has always pushed against the limits of the possible, often with breathtaking success. The quiet evidence suggests that our ancestors walked many roads to innovation, roads that later grew over and were forgotten. Our task is not merely to rediscover a single forgotten recipe, but to rebuild our appreciation for the vast, silent archive of human achievement. Every cracked pot, every rusted blade, every faded patch of pigment is a page from that unwritten library. They hint that the past is not a closed book, but a deep well of inspiration, waiting for the light of a new question to reveal wonders we have not yet even dreamed of. The greatest material discovery of the 21st century might not be invented in a lab, but patiently deciphered from a clue that has been resting in the earth and in our museums for thousands